Right. So we we can now do glycolysis, but usually biochemistry it's not all about these words. You need to know the process, the actual processes that are happening at cellular level for you to know the enzymes that are working, the end products of each. Um, so basically, you also use Greek, same with anatomy, right? Glyco meaning you have something that's sugary. Lysis, it's breakdown. It's a bit different from gluconeogenesis, where genesis, it's actually we are forming in the beginning. So lysis, there is breakdown, and the other name
Yes.
for glycolysis is the Emden-Mayanoff process, right? And what we basically get from glycolysis, or rather, to summarize what glycolysis is, you basically have a glucose molecule. Then you have phosphorylation, you have your ADPs and everything, giving rise to two pyruvate molecules. So you get two pyruvate molecules and you get two ATP molecules as a net result. Those are the main things that you're going to get. So you're going to get pyruvate, then you're going to get two ATP molecules, then you also get two NADH molecules. Right? The other things that you get include things like your protons and the likes. But I just wanted to know that in overall, as a net result of glycolysis, you're just simply using glucose. You are breaking down glucose to get pyruvate and ATP. But what we really want in this process is pyruvate. Do you by any chance know why we need pyruvate?
Sorry.
Do you by any chance know why we need pyruvate?
Uh, I think for the for so that it mixes with
So you
huh?
so you
So
basically
that it will be able to end the cell.
the Krebs cycle, right?
Yes.
So you need pyruvate to later on mix with your acetyl CoA. Then when they mix, you get citric acid and the likes, and that basically becomes your Krebs cycle, your tricarboxylic acid cycle. So the, for the substrate of that cycle, it's coming from glycolysis, and that substrate is going to be what? To be pyruvate. So far, so good.
Yes.
Okay. So I prefer to break down glycolysis into three stages. I know this slide is a bit busy. It was made by medical students that use it, but I prefer to break it down into three. Right. Um, in terms of the key roles here of glycolysis, I would rather use number two here to say that it's basically there to produce pyruvate, which we need for our TCA cycle. Energy production, yes, but remember we said we only produce two ATP molecules, and two ATP molecules is a net result. That's nothing. So yes, there is energy production, but well, it's just two ATP molecules. Anaerobic respiration, metabolic flexibility, well, yes. But the main role or the main thing that we're getting here is the substrate that we need to use in the TCA cycle, right? So far, so good.
Yes.
Okay. So there are three stages in glycolysis. Um, if you're to look at the actual process, I think there are about 10, but those 10 can be broken down into three huge stages. So the first stage is we are starting with glucose. So what does glucose do? Glucose enters the cell because it can actually pass through um, the cell membrane. So glucose can pass through the cell membrane. But now this cell should be able to retain this glucose in the cell so that it doesn't go out again. So the first stage, I want to achieve two things. I want to be able to trap glucose inside the what? Inside the cell cytoplasm. Number two, I want to destabilize this glucose molecule so that it can undergo reactions in the second stage. So the first thing that happens is I have a glucose molecule in the cytoplasm. This glucose molecule will react with ATP. And when it reacts with ATP, I'm going to add a phosphate molecule on the sixth position of your carbohydrate moiety. So you get glucose 6 phosphate. So I have reacted glucose with an ATP molecule. So basically, this is a consumption stage. Why am I calling it consumption stage? Because we are actually using ATP molecules. We are not yet producing. So we are still consuming these ATP molecules. So glucose reacts with ATP, then you get glucose 6.
Sorry,
Yes.
I lost the connection.
All right, that's fine. So I was saying that in the first stage, right, you have glucose reacting with an ATP molecule to give you glucose 6 phosphate. Remember, I said you want to trap the glucose inside the cell cytoplasm, right?
Yes.
So if you add a phosphate molecule, remember phosphate is negatively charged. It's going to be your PO3 2 minus from your chemistry. So this simply means that you are not going to be able to you're not going to be able to allow this glucose 6 phosphate to pass through the what? The cell membrane because it is now negatively charged. If you remember your cell physiology. So this glucose 6 phosphate will no longer be able to leave the cytoplasm. The enzyme that we use for this particular step is hexokinase. It can also be called glucokinase. The word kinase means we are phosphorylating. So whenever you see an enzyme being called kinase, we are basically what? Phosphorylating. So we have reacted glucose with ATP in the presence of hexokinase. Then we phosphorylated our glucose on the sixth carbohydrate moiety. Then we got glucose 6 phosphate. Right. So far, so good.
Yes.
Okay. Do you understand what an isomer is?
No.
I know you do. Isomer chemistry, things which you can actually form mirror images of each other, right?
Okay.
So what I want you to remember is, remember I said we divide glycolysis into three basic or three major steps. We are still in the first step. So once we form glucose 6 phosphate, this step, this first step that we're doing should give me something which, if we break down, I think I've lost you again. Okay, so now we're saying this for the first step, you have to be able to produce a molecule which can be broken down into two identical not identical, but two isomers, which have 3 carbohydrate moieties. Because glucose has 6 carbohydrates, but for the second major step, you want to break that thing down into a molecule with 3 carbohydrate molecules. So what do? We rearrange the arrangement of your carbohydrate moieties. So we use an enzyme called phosphoglucose isomerase. We are calling it phosphoglucose isomerase because we are isomerizing a molecule that is phosphate and glucose. So we basically then get what is called fructose 6 phosphate. It's just an isomer of glucose, right?
Okay.
So we started with glucose, then glucose in the presence of ATP and an enzyme called hexokinase. We made glucose 6 phosphate. In that process, we said we are consuming what? Energy. So we actually have a deficit of energy because we are using ATP. We don't just produce this glucose 6 phosphate, we also produce other things like ADP and a proton. Remember, ADP is the end result from taking a phosphate from ATP. Now we have glucose 6 phosphate. Glucose 6 phosphate in the presence of phosphoglucose isomerase, we produce fructose 6 phosphate. Right. Remember, we said we want to produce two identical.
Oh, sorry. Sorry. Is it my volume or it's your volume? I can't hear you properly.
It's probably your volume.
Oh,
Can you hear me now?
at a lower voice.
My it's either your network or your device, maybe. I'm not so sure.
Let me try to fix out the volume thing.
Okay, great. So we moved from glucose 6 phosphate to fructose 6 phosphate. We're still in the first major step that I'm talking about. And remember, I said the second step that we're going to then do, we want to break down this molecule into two isomers. So at this point, we only have one phosphate molecule. So if you're going to break it down at this point, it won't work because you only have one phosphate. You need to have two phosphate molecules. So that means we need another enzyme, which is a kinase. So this kinase, this time around, it's a phosphofructokinase. It's also going to use ATP because we want to take that phosphate molecule, right? So now what you then form is called fructose 1,6-bisphosphonate. Now you have two phosphate molecules. So basically what I'm saying is the first step that I'm talking about is ending here. The first major step is ending here, and we have fructose 1,6-bisphosphonate. This is a molecule that cannot go through back, and this molecule is not stable. So it can then undergo the reactions of the second step. Right. So far, so good.
Yes, sir.
Okay. So now for the second step, remember I said we want to break down this 6 carbohydrate molecule into a 3 carbohydrate molecule, or like a 3 carbohydrate moiety. So you now need an enzyme that is called an aldolase. Do you by any chance remember what an aldol reaction is in chemistry?
I can't remember, sir.
Usually it's carbon to carbon bond formation, but I usually don't like teaching people to those levels. But what you have now is your fructose 1,6 bisphosphonate. It's going to be acted upon by aldolase. And what aldolase does is, I'm not really liking how they put this diagram across, but what it simply does is it produces two molecules that have three carbohydrate moieties. The first molecule is called DHAP, which is this one, dihydroxy acetone phosphate. So that's DHAP. The second molecule, which also has three carbohydrate molecules, is called GAP. So GAP is also referred to as what? Glyceraldehyde 3-phosphate. What we want for the final process of glycolysis is GAP, which is glyceraldehyde 3-phosphate. So what this reaction is simply doing is it's giving us one GAP and one DHAP. So I need another enzyme, which is an isomerase, to change the DHAP into what? Into GAP, so that the overall reaction is I end up with two glyceraldehyde 3-phosphates. So I'll take that again. I had fructose 1,6 bisphosphonate from the first major step. Then now we're getting an aldol reaction, and we are converting this 6 carbohydrate moiety into a 3 carbohydrate moiety. And now we form two molecules. One is GAP, which is glyceraldehyde 3-phosphate, which we need for the next reaction. Then the other one is dihydroxy acetone phosphate. This moiety is not what we want for the next reaction. So we need another enzyme to convert it to GAP again. And that enzyme is going to be isomerase. So the end result of this step is I'm going to get two glyceraldehyde 3-phosphates. Making sense?
Yes, sir.
So this isomerase, you can actually call it triiose phosphate isomerase. This isomerase, that's changing your DHAP into GAP. So you now have two GAP molecules. Great. Now we want to move on to the last stage of glycolysis. So the last stage now you have GAP here. So what GAP does is it reacts with NAD plus. Where's my cursor? Here. So it reacts with NAD plus. Right. But this diagram, the reason why there are twos here is, remember, you now have produced two GAPs. Right?
Yeah.
So GAP will react with NAD plus. You also react with a phosphate molecule here. Though it's not put on the diagram, you also have a phosphate molecule there. Right. And the enzyme that's working here is a dehydrogenase. So it's called GAP dehydrogenase. From glyceraldehyde 3-phosphate, you're going to get 1,3-bisphosphoglycerate. Why are we saying 1,3? Because remember, in my equation here, I've added a phosphate molecule. So that phosphate molecule is the second phosphate molecule that you are getting in what? In your carbohydrate moiety. So you add a phosphate molecule, it becomes 1,3. Initially, we just had a phosphate molecule on the 3 position. Now we have a phosphate molecule on the first position. Then we removed an H plus ion, right? Because remember, we reacted NAD plus here. Now you have NADH. Are you seeing that?
Yes, sir.
Right? So an enzyme that is called a dehydrogenase is simply an enzyme that catalyzes removal of an hydrogen atom. So you have removed a hydrogen atom and you have placed it on a different location, and now you form NADH. So now the end result from this step is GAP. From GAP reacted with GAP dehydrogenase in the presence of NAD plus and a phosphate molecule. Then you form 1,3 bisphosphoglycerate. When you form this 1,3 bisphosphoglycerate, there is also going to be another end product, which is NADH. And please remember, these things like NADH, they are also substrates for other important molecules, other important steps rather, not molecules. So for glycolysis, we are now at 1,3 bisphosphoglycerate, right? Are you still there?
Yes, sir.
You're still there. Great. Then from here, there's an enzyme called phosphoglycerate kinase. This one is a bit different in the sense that I am now removing phosphate molecules. So instead of using ATP, I am now making ATP. So you have two molecules of 1,3 bisphosphoglycerate. Then you have a kinase enzyme that's removing, firstly, the first phosphate on the first carbohydrate moiety, and that phosphate will go onto the ADPs, then you make ATP. So you'll be left with 3 phosphoglycerate. Right? Then, hello, you're still there, right?
Yes, I'm following.
Then from your 3 phosphoglycerate, you're going to get a mutase which simply changes the position on which your phosphate molecule is. Initially, the phosphate molecule was on the 3 position. It's going to change it to go to the second carbohydrate moiety. So you then form something called 2-phosphoglycerate. I'm forgetting most of the specifics for that, but a 2-phosphoglycerate molecule is the one that you can convert to something called phosphoenolpyruvate. The enzyme that you need to use for that is called enolase, right? So this step here is a reversible step. So remember, chemistry, you can have a step going forward. The step can also go backward. It's also the same for all those other processes, but I want you to take note of this one in particular, that it's a reversible step. Right? Hello?
Yes, sir. Yes, I'm following.
So, so what enolase does is it would dehydrate this 2-phosphoglycerate. So you're going to dehydrate this 2-phosphoglycerate, then you form PEP, your phosphoenolpyruvate, right? And if I remember well, the textbooks will tell you that this PEP is a high energy molecule. And by high energy molecule, we mean when we are going to react it, we are going to get ATP molecules again. So when you then react phosphoenol pyruvate, you use an enzyme called pyruvate kinase. Remember, when you have the word kinase, you're going to be either adding or basically dealing with phosphate molecules. You're going to add or remove. So pyruvate kinase is going to remove the last remaining phosphate moiety, and you get then you get pyruvate. Now notice we have made two ATP molecules here. We have made two ATP molecules there. But in the beginning, I used two ATP molecules. So the net production of ATP, you're going to have two ATP molecules. That's why when I started, I said the net result of glycolysis is you get two pyruvate molecules that are going to be ushered towards the TCA cycle, better known as the Krebs cycle. Then you get two ATP molecules as a net result. You get two NADH molecules that are coming from the dehydrogenase enzyme, your GAP dehydrogenase from this step. Because remember, we said a dehydrogenase enzyme catalyzes or rather facilitates the removal of a hydrogen atom. Right. So I'll summarize this again. We started with glucose. Then in the presence of hexokinase, we phosphorylated our glucose on the sixth carbohydrate moiety, and we produced glucose 6-phosphate and an ADP molecule, as well as a proton that is not on this diagram. Then we wanted to trap our molecule into the cell. Now we want to destabilize it. We used an enzyme called phosphogluconase isomerase, and it converted our glucose 6-phosphate into fructose 6-phosphate. Now, because we want to form two identical 3-carbohydrate moieties, we need another phosphate molecule. So we're going to get another kinase, which is called fructokinase. That is now going to phosphorylate on the first carbohydrate moiety. Then we get fructose 1,6-bisphosphonate. From there, we then talked about the aldol reactions, and we formed two molecules, GAP and DHAP. But I said we don't need this DHAP for our final step. We need a GAP. So we're simply going to isomerize this DHAP to form another GAP. Then we end up with 2-glyceraldehyde 3-phosphates. Then we got an enzyme for this step, which is called GAP dehydrogenase. In the presence of a phosphate and NAD+. Since we added a phosphate, we then formed 1,3-bisphosphoglycerate. And since the enzyme was a dehydrogenase enzyme, we removed a hydrogen atom from the NAD+ and we put it onto our NADH. Then we basically formed 1,3-bisphosphoglycerate. So we have two of them since we reacted two GAP molecules. From the 1,3-bisphosphoglycerate, we got an enzyme that was called, so this was a high energy molecule. We are going to release two ATPs thanks to an enzyme called phosphoglycerate kinase. We can skip all this, and remember I said we need a mutase enzyme to change the phosphorylation from the third moiety to the second moiety. So when you then get phosphoenol pyruvate from the removal of water from these 2-phosphoglycerate using an enzyme called enolase, this is the last high energy molecule in this in this pathway. So that PEP can then be acted upon by pyruvate kinase to release the last two high energy or rather energy molecules, which is ATP. And now we have formed 4 ATP molecules at the expense of using 2 ATP molecules. So the net result is what? Is 2 ATP molecules. So the formula for glycolysis, if I'm to simplify it, you start with glucose, then you add 2 ADP molecules. This is the net formula. We are not adding ATP because we want to put 2 ATPs at the end. You add 2 NAD pluses, then you add 2 phosphates. Then what do you get? You get 2 molecules of pyruvate, which are these ones at the end. You get 2 ATP molecules as a net result. Then you get 2 NADHs from this dehydrogenation reaction. Then you also get 2 protons. So my belief is we have talked biochemistry. So these slides can give you a breakdown of what we're talking about, but it's simply now putting pictures into place. So here we started with the glucose. We reacted it with an ATP molecule in the presence of an enzyme called hexokinase. Then we phosphorylated on the 6th carbohydrate moiety. Then we formed something called glucose 6-phosphate. Then we got isomerization to make another molecule called fructose 6-phosphate, which is not stable. Then we added another kinase. Then we formed fructose 1,6-bisphosphonate. So all of this is still the first phase. Remember, we said there's a consumption phase. I prefer calling it the consumption phase. They use the word investment, but it's the same thing. We are consuming energy for now. Then the second stage is called cleavage. So in cleavage now, I don't know why they still put it as the first phase, but the second stage is what we call cleavage. Now you are breaking down your fructose 1,6-bisphosphonate into 2 3 carbohydrate moieties, DHAP and GAP. But remember I said we only want GAP. So this DHAP should be converted to another what? To another GAP, so that I now have 2 GAP molecules. Then I enter the last phase of glycolysis, where I now start to make energy. It's called the energy payoff phase. But the main reason why we're doing glycolysis is not really for energy, but we want what? We want your pyruvate for the next thing that we're going to discuss today, which is the what? The Krebs cycle. So now this is the third stage. Remember, we said we start off with the glyceraldehyde 3-phosphate. Then in the presence of a dehydrogenase, I'm going to remove a hydrogen atom and place it on NAD plus. Then I form NADH. Then I'm going to phosphorylate again this to give us glycerate 1,3-bisphosphonate. That's why I said in that reaction you add a phosphate. Then when you now have glycerate 1,3-bisphosphonate, you're going to get a kinase, which is going to remove phosphate. So this is the first step where you produce ATP. Then remember I said we then isomerize to a 2-phosphoglycerate. This is more of a summary. Then we remove water using an enzyme called enolase. Then you produce PEP. PEP is what is called phosphoenol pyruvate. This is very important because this phosphoenol pyruvate is the last high energy molecule. So it then releases its ATP, its phosphate moiety to ADP. Then you make an ATP, which basically then produces more energy. Right. So this is the net reaction. But for you to understand this net reaction, you need to do it like the chemistry way to end up with this. But you are now more of a medical student. I'll assume you understand how we got to this. In the first side, we have removed the ATP molecules. We had 2 ATP molecules on the last side. we had 4 on the other side of the equation. So it's a net, you're left with 2 on the other side. So you started by investing ATP, then you ended up by producing what? By producing ATP. Right. Okay. Do we have any questions on glycolysis?